Hi. Okay, so why is there so much stuff about statistics on this channel? You might have noticed that there is a lot of material about statistics on this channel. Why? Isn't this a physics channel? Yes and no. The focus of this channel is on concepts used in physics research. It's not focused too much on what we know of the laws of nature, but instead on how we know what we know of the laws of nature. In physics research, we're trying to discover new laws of nature. And that means there are some things we need to do. We need to make hypotheses to explain phenomena in the natural world, conduct experiments to test those hypotheses, interpret data that we get from those experiments, and report our results. So here, the emphasis is on methods. How physicists test hypotheses, how they interpret data and draw conclusions from it, how experimental results are quantified, and how to make useful models of phenomena. That last one is an important skill in research, but also critical in applications as well. But if you're here to learn physics and not statistics, don't worry. There are also a lot of physics results on here as examples. So come for the physics, stay for the stats. And more generally, this channel discusses a lot of statistical tools to show how we can use these tools to learn about the world around us. In this video, we'll give a brief overview of some of these statistical concepts and briefly describe why they show up so often in physics research. The topics mentioned here are covered in detail in other videos on this channel. Okay, first let's talk about some concepts that show up directly in physics results. We're interested in the Poisson and Gaussian distributions and the closely related binomial distribution. Let's start with the Poisson distribution. Let's say you have a radioactive sample and you want to know how many decays will happen in the sample in the next minute. To a very good approximation, that is described by the Poisson distribution. And it's critical to almost every particle physics experiment. Let's briefly consider a hypothetical collider experiment. In a collider experiment, we take particles and collide them so they interact. When they interact, other particles can be created. These can be detected by a particle detector. When a collision produces a set of particles registered by the detector, this is called an event. We then measure the rates of these processes and see if they agree with predictions of hypotheses. The number of events of a certain type observed in an experiment is well described by the Poisson distribution. So the Poisson distribution is intimately related to most particle physics results that you hear about. Okay, next let's talk about the Gaussian distribution. It's also called the normal distribution. We'll mention two places it comes up. First, in the case of a large number of events, the Poisson distribution that we just discussed approaches the Gaussian distribution. So that's the first place. The second is related to measurement errors, which we'll now discuss a bit. Okay, so we measure quantities in nature. This can be something like the distance to a star or the mass of a particle. Due to measurement errors, the measured values that we get for these quantities are not equal to their true values. Under some reasonably common experimental conditions, the relation between the measured and true values of a quantity are approximately described by a Gaussian distribution. The measured value will tend to fall near the true value and only rarely fall far from it. So the Gaussian distribution is important for understanding how the true values of quantities translate into what we see in actual experiments. We can use it to determine just how well or badly a measurement agrees with a given hypothesis. Both the Poisson and Gaussian distributions show up in a lot of contexts, not just physics. If you want more information, check out the Poisson statistics playlist, the Gaussian statistics playlist, and the playlist entitled Brief Introduction to Gaussian Errors. And lastly, let's just mention the binomial distribution. If you want to understand the Poisson or Gaussian distributions, a good place to start is the binomial distribution. You can check out the Binomial Statistics playlist for more info. Okay, now let's just talk a little bit about how statistics concepts pop up in the ways we quantify and report experimental results. Scientists make hypotheses and experimentally test them. But when we get an experimental result, we don't just report that it agrees or disagrees with a given hypothesis. Instead, we also say how well it agrees or how badly it disagrees with that hypothesis. This means that we need ways of quantifying how much an experimental result agrees or disagrees with a hypothesis. For example, under a certain hypothesis, how strange is a certain experimental result? This is where some concepts from hypothesis testing come in. Examples of some of these concepts include confidence levels, p-values, and statistical significance. For more information, check out the Hypothesis Testing playlist. Lastly, let's mention Bayes' theorem. Let's say we measure some quantity and we get a measured value for that quantity. What does that tell us about the quantity's true value? In particular, we may want to ask for the probability that the true value of this quantity lies in some specified range. To answer that, we need Bayes' theorem. You can check out the Bayesian playlist for more information. Okay, let's very briefly summarize. In physics research, we form hypotheses and test them in order to uncover new laws of nature. Concepts from statistics are important for the necessary data analysis. The videos on this channel are color-coded according to content, so for more stats content, check out the videos with purple backgrounds.